So let me maybe just before I start. Well, first of all, I promise that I will not make jokes. I will try to be more intense. It will be not that amusing as before. And probably this is the last joke. Let me tell you, maybe just stress out 2 points which Vladimir did not tell because he did not have time for that. So there are some differences. How do we produce the functional space? So suppose we have a graded vector space, Vi, where I belongs to Z, and we assume that zero part is not present, but it's not important. So first of all, we take V star, then consider the symmetric algebra of V star. And this is symmetric algebra over the ground ring because they are assumed to be 3 modules for the moment. And this is not the algebra we need because these are polynomials. We need to make formal power series out of this. So and there are 2 different filtrations on polynomials. So the one filtration, number 1, we consider let's call F tilde P. The symmetric of V star are polynomials of degree greater than P, for instance. And this algebra will survive under the change of coordinates. I mean, these ideals will survive. So we can still do the same. We can produce the projective limit of this. So the symmetric V star over Fp tilde symmetric. What we'll get will be the formal power series in the usual sense. We can do this not for the whole symmetric, but for those which are of degree I, right? And then we'll produce the graded formal power series, which is just the direct sum of power series of fixed degrees. So in general, it's not a direct sum, it's a direct product. Because in general, formal power series is not necessarily a sum of formal power series of homogeneous degree with respect to the gradient. But we can do this by force. We can just force it. And the other filtration is the one which Vladimir explained to us. So this is the polynomials. Okay, this is the ideal generated by. So this is the polynomial degree. And this is by the degree with respect to Z gradient. Or let's say greater or equal to P. Or less or equal to minus P to be consistent with the previous one. And we can play the same game, consider the projective limit over the symmetric V star, degree I, modulo this Fp, the symmetric V star. And if our Z vector space is Z graded, but the degree is bounded either from below or from above, this will be the same algebras. So that's what we call this formal power series. But if it's not true, if we allow all possible degrees from minus infinity to plus infinity, this algebra will be different. For instance, here, the low combination, suppose we have coordinates of degree x minus 3, x minus 2, and so on. This is of degree minus 3, minus 4, minus 5, and this is unbounded. X minus 1, sorry, x minus 1, x plus 1, x plus 2 of degree 1, 2, and so on. Then the following combination, xi, x minus I for I greater than 0, is not a formal power series in the usual sense. Right? Because it's a square, it's quadratic, but it contains many terms. But it will be the formal power series in this sense, and it's allowed. So then this is the difference. And this, besides producing different results, also this filtration, which is different from the usual polynomial filtration, this allows to prove more theorems. For instance, the Batchelor theorem can be proved in more generality. We see we see, for instance, this n cross n structure immediately because of this filtration. So for that graded case, this one is more powerful. And just another remark also from the previous talk is the following one. Just remember that we proved, not proved, but it was mentioned and almost proved that every formal power series and we can assume that there's only finite number of generators, or finite number of coordinates. For the infinite number, it's somewhat more complicated, what I'm saying. So let's take a formal power series of generators of coordinates of 0 degree, then there must be smooth and formal power series with respect to non-zero degrees. Then what Vladimir said, it can be written as the sum, finite sum of monomials of degree not equal to 0 variables whose coefficients are formal power series of degree 0. Of z degree 0. This is what Vladimir said, right? And just to prove this, one needs to solve some system of linear Diophantine equations. And for this system, very, very similar theorem to linear algebra, what we can expect holds. Because in linear algebra, when we solve the system of non-homogeneous linear equations, it's usually the solutions some solutions to the homogeneous plus solutions to homogeneous. Right? And for the solutions of homogeneous, you have a basis. This is how it works in usual linear algebra over fields. Over Z, it's almost the same. If you produce over Z plus with positive integers, it's almost the same, except this is not a basis, these are generators. And this, of course, the proof is more complicated, but we can still use it. And how to apply this statement? So one of the applications was already mentioned by Vladimir. We shown that one functional space gives another one. But this is somewhat more powerful. Actually, this also shows why we call this manifolds we produce semi-formal. So the Batchelor theorem can be, in the Z-graded case, can be reformulated in the following way. So there exists some supermanifold with some Euler vector field, which is a gradient, such that our M0 base is embedded here, and our Z-graded manifold is a formal neighborhood of this 0 degree submanifold here. And then, so this is another formulation of the Batchelor theorem in finite dimensions. And then this allows to prove the following fact. So we know that in general, in jet technique, there is what is called Borel's theorem, that any formal power series is a Taylor expansion of some smooth function. It does not work in the analytical case because we do not require any convergence. But if you require smoothness, it works. So this is really, whenever we have some sequence of numbers, we can produce a smooth function such that this sequence of numbers are the derivatives of a given point. Or on a submanifold, then we take the Taylor series in the transversal direction. And this representation helps to prove that the Borel's theorem also holds in Z-graded case. So whenever we have here some formal power series or some fixed Z gradient, it's possible to find a smooth function in local neighborhood of the same degree, Z degree, such that the formal series is the Taylor expansion. In general, it's not obvious why that's so, but this helps to prove it. Because we reduce everything to 0 degree and to polynomials of non-zero degree variables. Okay, this is what, these are two remarks about the previous talk. And now let me start with another part. So the preliminary plan is the following. So this part will be devoted to graded Lie algebras and graded Lie groups. So it's subtitle. And first, I will give you, just to show that this is non-trivial theory, so they're really nice Z-graded Lie algebras. I will give you some example of Z-graded Lie algebras. Second, I will come to the notion of integration. So whenever we have a Lie algebra, that's the Lie question, but it exists a group which integrates it. So for finite dimensional Lie algebras, it's the Lie theorem. For graded Lie algebras, there are different kinds of integration. I will discuss both. So actually, there are two different ways of integrating. So one is what is called Harish-Chandra pairs. And another one is, let me call this a global theory. I will explain what it means. Which, by the way, may also employ Harish-Chandra pairs, but that's somewhat different context. Okay, and number three, if time permits, if not, then I will answer two questions. I will explain how to do similar things in the algebraic context. Namely, this will be some speculation on, not speculation, about Harish-Chandra pairs for Lie algebroids, which is, I guess, not known. At least in our third paper mentioned by Vladimir, this is completely explained for action Lie algebroids, but there's also idea how to do this in more general context. Okay, so now let me come to the scientific part of this. Oh, okay. So, by definition, a graded Lie algebra and by gradient I will mean Z-graded in this talk. It's a Z-graded vector space in the above sense, which is probably a superspace. So here we have the degree, which takes values in Z, and the parity, which takes values in Z2. And in general, the parity is not necessarily the degree modulo 2. In some cases it is, but in general, what we require is that each GI is super. So they are compatible, so the two gradients are commutant, but that's not necessarily one is reduction of another one. Here we have G01, yes. I belongs to that. So it means that each GI is a super vector space. And then we require that there is a bracket, which is graded commutative. Graded commutative in the usual sense, x, y equals to -1, 1 plus the parity of x times the parity of y, yx, plus the super Jacobi condition, which I personally prefer to reformulate in such that the left adjoint action is a super derivation. It's the easiest way. Right? So the x. Degree of this bracket is 0. I did not say this yet. So it's even. In the super Lie algebra, it's by definition even because it's a super Lie algebra. But with respect to, okay, it's degree 0 with respect to that gradient, which means that GI tensor GJ will go to GI plus J. But here, so the rule is x, y, z equals to x, y, z plus -1 the parity x, the parity of y, x, z. This is the non-symmetric way, which shows that the joint action is a super derivation, the way I like. And in addition, we require that the bracket has, so the bracket has degree 0 with respect to the z gradient. So let me give you some examples. And actually, in this example, I will show that this condition is not required in general. Right? So it can be different. So suppose we have they are commuting, but they not that one is a reduction modulo 2 of another one, but they are commuting. So it means each GI is a supervector space. The Lie bracket is even. Okay, the Lie bracket is even with respect to Z2 and degree 0 with respect to Z. In both cases, degree 0. Yeah, it's skew-symmetric with respect to the parity, yes, because it's a super Lie algebra. Yeah, this is the super Jacobi. Yeah. Okay, so the example number 1. I do not want to produce trivial examples like usual Lie algebra is a graded Lie algebra, but it's not what we like. So suppose we have just a funny story. Suppose we have a Z-graded Lie algebra in the usual sense. So the parity is always 0. For instance, there's a nice example SL2, right, with generators E, H, and F. So it's a linear combination, right? It's a linear combination of this with the relation EF equals to H, HE equals to 2E, and HF equals to minus 2F. So it's a well-defined graded Lie algebra with 3 terms, so such that G minus 1 equals to R, let's say, over R. F, G0 equals to RH, and G1 equals to RF, RE, and the gradient is given by the joint action of H. Right. So, and this is a graded, it's a nice example for graded Lie algebra, which is not super. So, in principle, all semi-simple simple Lie algebras can be viewed as graded in many different ways. So this is subject to what is called Cartan geometries. But here, there's a nice way how to produce out of it a super graded Lie algebra. We just take phi g, which is phi g plus g. With this one will be now odd, this will be now even. So it's a new g, let's say tilde, such that the j tilde equals to pi ji plus ji. So we just leave gradient, so this can be viewed as a shift of parity of the cotangent, of the tangent space. So we can lift the gradient to the tangent space just in the usual way. So now it becomes super, right? So at each degree I, we have a super vector space. And there's a simple way how to produce the bracket. We just leave the bracket. So this acts on that. Here the product is 0. Here this one acts on that by a joint action. This here on G, the old bracket. Usual. So example number 2. Suppose we have G a super Lie algebra. For instance, this is GL of a super vector space. Then we can apply the same trick. Take G1 shifted by 1 plus G, and then this will be a degree Z-graded Lie algebra, where this one will be in degree minus 1, this will be in degree 0, and the idea of the bracket is the same. So here the old bracket, here the joint action, and here the bracket is 0. But now you see, now it's super, right? Both are super. But there are more examples, and all of them are interesting. So let me, so there are other natural examples like vector fields, endomorphisms. So the Lie algebra of a graded vector space, it's again graded. But let me show you two more examples, or one big example and two examples of this example, which is called the Tanaka Prolongation. So it's another example, which is called Tanaka Prolongation. And this works as follows. Suppose we have a negatively graded Lie algebra. So this is the sum of gi for I strictly less than 0. So there are many possibilities. I will show at least two when it happens. But for instance, you can take the lower degree, upper lower triangle matrices. This will be also Z graded with such a type of gradient, only negative. So now out of this, we can construct a Z graded Lie algebra. And the construction is canonical. So we can add degree 0, degree 1, and so on parts in the following way. So up to degree, so this will be n plus, so up to degree minus 1, it's the same n. And starting from degree 0 to infinity, we have to add additional terms and make a Lie algebra out of this. So then the idea of G0 is pretty simple. So we have a graded Lie algebra, which is negatively graded. And look at derivations of this Lie algebra of degree 0. Right? So these are derivations of degree 0 of n. First of all, it's a Lie algebra itself. Actually, I do not require anything for the moment. I assume that it's purely even, but it can be also super. It's not important because for the prolongation, the idea is the same. But it assumes that everything is even. Then G0 is simply derivation. It's a Lie algebra, which we put in degree 0. So, and then it's obvious that if we add G0 to n, this will be a Lie algebra, right? Because G0 is a Lie algebra itself, and G0 acts on n because they are derivations. And n is a Lie algebra itself. So it's obvious that the first prolongation is a Lie algebra. We are here the old bracket. Here the Lie bracket of derivations, the commutative of derivations. And between these two, the action of a derivation on n. Now how to construct G1. So there's a canonical procedure. So G1 will be the set of derivations of degree 1. Which acts from n to n plus G0, and that's all. So in principle, it means that, well, here, let me add, just to be on the safe side, make everything simpler. There is some additional property that Gi minus 1 is totally generated by G minus 1, like this. Okay, so this is additional property which is required. Otherwise, the construction will be more complicated. It means that G minus 2 is the commutator of G minus 1 and G minus 1. G minus 3 is G minus 2 with G minus 1, and so on. So everything is generated by G minus 1. So the whole algebra is generated by degree minus 1. So now D can be viewed as a system of maps from G minus I to G minus I plus 1 for I greater than 0. And then for the derivation, we can just say what the derivation means. They're just the same property. So d of the bracket xy equals to dxy plus minus depending on the sign, but let's say all the signs are plus, x dy minus I plus 1, of course. So how it acts? So if I greater than 1, then what it will be, g minus I. So this will be actually, yeah, g minus I will go to g minus I plus 1, but it will be still inside n, right? Because if I greater than 1, this will be less than 0, so it's still inside n. But the last possibility is from g1 to g0. But here we know how, so suppose x, for instance, x belongs to g minus 1 here, then dx must be an element in g0. But we already know how g0 acts on g minus 1, for instance, so the other g's. Right, so we can still write the derivation property. Okay. So this property makes sense. And then we can extend the bracket to, so then now we extend the bracket to the bracket between g0 tensor g1 to g0. And this is simply the commutator. So g0 preserves n, g1x from n to n plus g0, and we can write the commutator of two derivations. So this will be the commutator of two derivations. And now, inductively, if you do this by induction, if we are careful enough, we will produce G2, G3, and so on, just by use of the same procedure. First, we write derivations, then we write the bracket as the commutator of two brackets, using the previous bracket which was defined before. So if you do this carefully, you'll see that it's possible to define inductively the bracket of the whole sum, such that the whole G, which is the sum of G I from Z, which is n plus g0 plus g1, and so on, will become a Z-graded Lie algebra. And now let me give you two examples of the example. So let's say this example. Yeah. Mm-hmm. And canonically extend. So that what is important, actually we can do this even without that. But it's nice when such a property, which is the upper one, holds. Then actually everything will reduce to some tensors on g minus 1, because everything is generated by g minus 1. And I will show in the example how it works now. So it's yeah, again, right? So again, minus, of course. It's an assumption that ON is generated by G minus 1. For instance, if you take lower triangular matrices, it will be true, right? So everything will be degree minus 1. Yeah, G2 and degree 2, derivations of degree 2. And whenever we have all data completed up to order P, we can do this the order P plus 1. Mm-hmm. Now I will show two examples, which are, of course, very familiar to you. And probably the last one is also familiar to those who are working on Leibniz algebras. So example 3.1. So let us assume that N is just a abelian Lie algebra concentrated in degree minus 1. Right? So the bracket is 0. And everything is degree. So it's a graded Lie algebra of negative degrees. Then how to produce G0? Just your guess. So there are no relations, no extra relation will appear. This will be simply GL of V, nothing else. Yeah, GLV, which is V tensor V, right? V star. There's nothing else because you can see that every element here will give you a derivation of such a bracket. because the bracket is just 0. But with G1, it will be more complicated, right? So G1 has to be homomorphisms from V to G0. So this should be derivations. This is G minus 1, right? Should be derivations with which variation G minus 1 to G0. So, okay, let's say this is inside, right? To be on the safe side. This is inside, which is isomorphic to homomorphisms of tensor 2V to V, right? Just by using of G0. Because G0 is homomorphism from V to V, and we put one more variable, right? So this will be bilinear map from V to V. Okay, but this is not the case. I mean, it's not all possible maps will give us derivation. So let's see. So suppose we have phi, and then the property. Just if you require this derivation, you immediately see that such a map should be symmetric. Because for the derivation, it will be something like phi phi V1 V2 minus V2 phi V1. I'm sorry, it's not correct. Anyway, it's a simple exercise to see that the property that for every V1, V2 from V, the bracket gives 0, immediately implies that G1 equals to homomorphisms from S2, V to V. So it must be symmetrical. Then we continue. So you guess what do we get at the order K? Just by the same idea, we'll obtain homomorphisms, homomorphism from Sk plus 1, V to V. Okay, and then so the whole holy algebra will start with V, then plus GLV, right? Plus, let's say that we are in finite dimensions, S2 V star V, plus S3 V star tensor V, plus, and so on, plus all polynomial powers of V star cross V. So do you recognize this algebra? It will be Z-graded algebra, which I guess everybody can recognize if you just think more than the time required. So this will be a form of vector fields. And these symmetric powers will be precisely Taylor expansion, Taylor coefficients of formal vector fields. So, and then let me show you one more example, which is again about this Tanaka prolongation. This will produce a more interesting algebra, which is where we drop one of the conditions. So let me drop the condition that the nilpotent algebra has only one term of degree -1. So suppose we have a vector space. Let's put this in degree -1. By what? Yes, right. On vector fields on V, yes. Around at the 0, yes. So this will be the derivations. This will be the Taylor coefficients. Yes, precisely. Endomorphisms, linear vector fields. And then degree 0, of course, right? Because quadratic vector fields in degree 1, right? Yeah. With and the gradient will be given by the Euler vector field, by the standard one. Let's take a vector space, probably a super vector space, because in many cases it must be super, and put it in degree -1. But as I said, this super is compatible with Z, but it's not the reduction modular 2. But for the moment, we can assume that it's even. It's not important. Then let's produce N as the following. So this is the Freely algebra generated by V. So it means that it will be negatively graded. In degree minus 1, it will be still the same V, right? So in degree minus 2, this will be the second exterior power. Just all brackets, then consider it independent with no relations. Then in degree 3, this will be something which is all triple brackets modulo the Jacobi relation and so on. So, and what we'll produce will be a negatively graded Lie algebra. So it's less or equal to 0 graded Lie algebra. Right, so each ni, or n minus I, will be the combination, linear combination of I brackets, brackets of length I, of elements in V, modular the Jacobi relation. So in degree 2, this is lambda 2. In degree minus 2, this is lambda 2. In degree 3, it's not all possible 3 brackets. We should take into account the Jacobi and so on. Okay, it's a negatively graded Lie algebra. Let's apply our magic technique, the Tanaka Prolongation. And what do we produce? So first of all, at degree 0, this is the same as in the previous example. Nothing can happen. So this is simply GLV. Or the same as V tensor, V star tensor V, right? If V is assumed that mentioned less than equivalence. Now, in degree 1, just remember that before we had something which is inside by linear maps from V taking values in V. But then we had an important algebra. We had the bracket of any two elements in this negatively graded is 0. And this gave a requirement that G1 is not a homomorphism from T to V, but a homomorphism from S to V to V. Just using this condition, we obtain some. And here it's not. There's no such a condition because it's a free Lie algebra. And it means, if you just look carefully, it will mean that this G1 will be homomorphism or homomorphism from T to V to V. But there are no constraints, so the bracket is free. Yeah, every derivation, so the free Lie algebra is generated by V. So every derivation of degree 0 is in one-to-one correspondence with endomorphisms of V. This is the nature of free Lie algebras, right? It's in the left adjoint functor, or right, I guess left, to the forgetful functor from Lie algebras to vector spaces. And this is just in the opposite direction. It's an adjoint functor. So it means that all linear maps of V will produce some automorphisms. So invertible linear maps produce some automorphisms of free Lie algebras, and all linear maps, not necessarily invertible, produce derivations. So every linear map of V can be extended as a derivation of the free Lie algebra. It means that, okay, so this is the same as in the previous example. But this is now new because we do not have any constraints. So what we produce is the whole bilinear maps from V to V. And now, if you do carefully, at the level K, we'll get homomorphisms from T K plus 1 V to V. And what is known, what we produce is known as the Counter Algebra. It's funny, it was written by ESI Kotov, the Soviet mathematician, at the very end of the 60s, before Tanaka introduced his Tanaka Prolongation. But he already knew this in some sense. And what is also good about this Counter Algebra, that, so the use of it, so the theory of Leibniz, homotopy Leibniz algebra is encoded Leibniz algebras is encoded by some derivations of degree 1 of this Counter Algebra. And in particular, just a usual Leibniz algebra, why the what is called Lodé differential is just a particular example of this one. Actually, how this bracket, it looks like a bracket of two vector fields with non-commutative coefficients. But in principle, the bracket is more complicated, it's more sophisticated. So it looks as follows. So suppose we have phi, which belongs to homomorphisms from T k plus 1 v to v, and psi, which belongs to homomorphisms from T l plus 1 v to v, and this is gk, this is gl. So now we have to produce a bracket, which must be an element in, it must be an element in G k plus L, which is the same as homomorphisms from T plus K plus 1 dV. And the idea is simple. Just we should be able to evaluate this on P k plus L plus 1 vectors. So let's assume that we have x1 and so on, x k plus L plus 1 from V. So then the bracket is the following: phi psi evaluated x1 and so on, x k plus L plus 1 equals to the sum for all I1 less and so on less than I L plus 1, I guess. Phi, here we should omit all vectors xi from these indices, L, L. And then on I L plus 1 position, we put psi of x I1 and so on, x I L plus 1 and so on. Minus the same with where psi and psi is exchanged. So it does not look like before. If you restrict ourselves to symmetric tensors, it will produce just the bracket of two formal vector fields. But otherwise, it's more complicated. It's a bracket of two derivations of the shuffle algebra. But and it's related to L infinity and all this stuff. But I will not explain it now. Okay, so now let me move to the integration problem. Yeah? Ah, right. So there are two. So before I explain the integration, I will tell you that that's how to integrate super Lie algebras. There is a nice technique which was proposed by Constant, which is the integration of super Lie by use of Harish-Chandra pairs. What it means? Suppose we have a super Lie algebra, so now it's Z2 graded. So this will consist of an even, let me write it like this to distinguish from Z gradient, 0 underlined. Even plus odd parts. Okay, so this 0 and 1 means parities. So they belong to Z2. Then suppose we know how to integrate. So what do we know about this pair? We know that G0 is at least even Lie algebra, right? So it's an even Lie algebra. G0 is acting on G1. So G1 is a G0 module. And there is also an additional bracket from G1 to G0. So it means that there's some additional property. But let us try. Suppose we know only how to integrate Lie groups, usual Lie algebras to Lie groups, only even, and modules over usual Lie algebras to modules over groups. Whenever we know how. Sorry? Strict in what sense? We do have Jacobi. It's a super Lie algebra. Like I defined probably at the very, very beginning somewhere in the talk. Yeah, it's everything. It's super skew symmetric plus super Jacobi, of course. Just super algebra. But it consists, so what data? No, we don't have Jacobi 8. We don't need it. Right, so the Jacobi 8 is 0. That's what you want to say. So how to view this pair? We just suppose we know only how to work with in the even case. It's an even Lie algebra, and it's an evenly module over the Lie algebra. Let's assume that we can integrate G0 to G0, just the usual Lie group. And the pair G0, G1, Lie algebra, its module, so the pair G0 underlined, G1 underlined, where this is a module over G0, just in the usual sense. Then we can construct the super Lie group. I do not have, of course, time to explain the theory of Hopf algebras, but we can construct this as a Hopf algebra. It's an algebra with a product, coproduct, antipode, and counit. And this algebra is the following. So we should take homomorphisms from UG, from the universal enveloping in the super sense of the whole super Lie algebra, taking values in functions of G0. I write functions to be on the safe side because this also works in the analytical case. That's what Lisa did Lisa Vishnikova did in her thesis. But this is not the whole. This should be also invariance under the action of UG0. And the action is pretty simple. So G0 is a subalgebra in G, and of course we can act by UG0 on UG, right? But how does it act here? This can be viewed as left invariant vector fields, right? It's just the usual even picture. And so the UG can be viewed as left invariant differential operators, right? So the whole makes sense. And this can be written as, for instance, if you reformulate, this will be maps from, so this will be maps from G0 underlined cross UG to say R, okay, such that they are linear with respect to the second argument. And also satisfy the clear condition. If you put something here, so suppose we have a pair consisting of G, which is an element in G0, and some element A, which belongs to UG. And now the idea that we can take a kind of product of these two, right? So it's not completely correct what I write, but it means that if you put X here, where X is an element in G0 underlined, this is the same, is equivalent to putting X here, right? So it's sort of associativity of the product. So how it was written before, it was more accurate, but I'm trying to give you the hint how it looks like. It looks like we take the product of G0 and UG, and totally honestly, it's better to view this as a formal subgroup, for instance, and take the formal completion of the formal group, and we take the product, and then because it's the product, so the element here is the same as the element inside here, and that's how it's written here. So we can put X on the right-hand side and X here either. So what we'll produce will be a Hopf algebra, and this Hopf algebra will produce functions due to the supergroup. So, and this is in one-to-one correspondence. I mean, there's an equivalence of categories of Harish-Chandra pairs. Namely, Harish-Chandra pair is a group, and the Lie algebra, which contains this Lie algebra as an even subalgebra, such that the group is acting on it. And the action integrates the adjoint action. Now, we can try to play the same game, but do the same with do the same with Z-graded algebras, and try to see what happens. So, do I have 15 minutes or 10 or 15? How much? Like this. So, so let me, now I will produce So, okay. Now, assume that we have a Z-graded Lie algebra. So G is the sum of Gi for I belongs to Z. We can write this as G0 plus the sum of Gi for I not equal to 0, right? And this is an even Lie, supposing the even situation. Or it's anyway, it's a Lie algebra concentrated in degree 0. And from the previous, we know how to integrate super Lie algebra. So this can be even super. But this is in degree 0. And this one is non-zero degrees. So this one is a module, so all that. Let's call this M, right? So M is a module over G0, right? And there's some additional properties, but we do not care about them. And now let us play the same game as before. So we know how to integrate G0, and we know how to integrate the action on G0 here. And actually, given that any Gi in both assumptions is finite dimensional, this is the same finite dimensional picture. We always know how to integrate. G0 preserve the degree here. So, and then what we'll get is a pair, again, G and G, where this is a degree 0, possibly supergroup. And this is its module, its graded module. And now we can play the same game, just produce the same sort of formula, right? But instead of 0 underlined, how it was, just an even algebra, we integrate G0. And we produce some Hopf algebra. So we, out of this data, so we obtain a pair G0, G, and we produce an algebra, A, which are homomorphisms in the same way over U, G0, UG with various functions on G0. We produce some Hopf algebra, which will be clearly graded because everything is graded. So there's a greatness coming from this. The greatness coming from this because this is of degree 0. So, and this will be a graded Hopf algebra. That graded Hopf algebra. And one can show that, well, I skipped the details, but just to show that we produce a good result, what we need to know is only Poincare-Bergov-Witt theorem, which holds here. Because the Poincare-Bergov-Witt theorem holds always when we have an ordered basis. We can find an ordered basis. But here, in such a case, we can find we can order it such that, for instance, start with G0, then G1, the basis of G1, the basis of G2, and so on. So Poincare-Bergov-Witt checked, so it holds. And the second, what we need to know is that actually the Poincare-Bergov-Witt in the symmetric form, or what is called in the Weyl form, preserves the coproduct. So namely, we can write an Poincare-Bergov-Witt isomorphism between SG and UG, such that this will be an isomorphism of co-algebras. So for algebras, it's not true because this is commutative. It's non-commutative in general. But for co-algebras, it can be done by use of the Weyl form, which just symmetrize. So take elements here, x1 and so on, xm, from G, and go to O1 over m factorial, the sum of x sigma 1 and so on, x sigma m inside UG, right? We just symmetrize. Then the symmetric monomials will come to symmetrized elements in the universal envelopment, and this will be an isomorphism of co-algebras. And this, just using the idea which was Vladimir did not have time to explain, but there was also some filtration of SF as great vector space as a co-algebra. And in fact, using this filtration, we can show that what we'll get here will be what we call a semi-formal, in our sense, Z-graded manifold. So super Z-graded, whatever. If we started with super, we'll get super. But actually, just to see what happens, it's sufficient to view everything as even. So the super does not bring too much. But for the super, we'll probably need to use Harish-Chandra again, but in a different context. just to integrate supergroup. But there's another way. So let us assume that we are in finite dimensions. So suppose the dimension of G is less than infinity. So the sum of all dimensions of Gi is less than infinity. Right? So it means the sum of all dimensions of Gi for I belongs to Z is less than infinity. In particular, only finite number of them are not zero, of course. So then we know how to integrate a finite dimensional Lie algebra or a finite dimensional super Lie algebra. And we obtain a Lie group or a super Lie group. Or super. Then what it is, how these two integration procedures are related. So first we obtain some semi-formal manifold, which is the base of which is G0, and then there are formal power series with respect to other coordinates of non-zero degrees. Or we obtain G. For instance, just let's come back to this simple example where G is SL2, right? It has in degree 1 E, in degree 0 H, in degree F minus 1 F, degree minus 1 F. So, and then we know how to integrate this. We'll get SL2, right? The good Lie group. Whatever, we can take SL2 as matrices, right? But on the other hand, if you integrate by use of Harish-Chandra, you'll get something weird. We'll need to integrate only the 0 degree subalgebra, which will produce R, and then some formal neighborhood around this. So there will be formal coordinates of formal power series with respect to other coordinates. So, but it does not look like SL2, right? And the result is that what we obtained is the formal neighborhood of G0 inside G. So one can prove this. So suppose we know how to integrate G to a finite dimensional Lie group. Then G0 will be inside a subgroup. We can take a formal power neighborhood, and what we'll get will be precisely the previous integration. In this case, yes. But in general, we have G, which is sum of G0 plus Gi for I not 0. Then we integrate by use of Harish-Chandra integrated context. Or if it's in finite dimensions, we integrate just in the usual sense, and we get G. And then this will be inside a formal neighborhood of G0 inside G, of a subgroup. So, and the group rule will be the formal group rule. Semi-formal, formal only in transversal direction. Yeah, it's a version of the Batchelor theorem, but in the group context, exactly. Yeah. Yes, yeah, sure. Sure, yeah, and this I can write just the morphism of two. The inclusion is given by a morphism of two Hopf algebras, and I can easily write this morphism explicitly. I can show this. In some sense. Yeah, but okay, it can be viewed as semi-direct because the transversal to a subgroup here exists. It's canonical, right? Because there's a transversal, there's a there's a complement to G0 inside. So there is a transversal of the group. So yeah. Yeah, it preserves. So the embedding here, so here we obtain this one. And what I'm saying that this is embedded inside G as a formal neighborhood of subgroup. So it means that there should be a map, should be a surjective map of Hopf algebras from functions on G to this Hopf algebra. One can easily construct this. Just take the formal expansion around the subgroup, and you precisely get this algebra. So, okay, if you, do not have too much time, so let me, I can answer two questions at the break if needed. So, let me just finish with another remark. What kind of structure appears on G, right? We started from a graded Lie algebra, and we integrated this to some group. If it's finite dimensional, then we can integrate this by use of usual technique. And what kind of structure on G? So we should expect that G is a graded in some sense, right? So it should be also Z graded. And the idea that this grading is given by use of the Van Est correspondence. So before we have a grading, so this is a grading on this graded Lie algebra, which can be viewed as a derivation, a certain type of derivations of degree 0. But not an arbitrary one, it should be semi-simple, right? It means that the whole G decomposes as the sum of eigen subspaces, and all eigenvalues are integers, right? So it means that epsilon on Gi evaluated to Gi equals to I times Gi. But one can easily show that this is a derivation. And then, by use of the Van Est correspondence, we obtain, and one can easily see that always true when G is simply connected, we obtain a multiplicative vector field on G, right? So the correspondence, in the case of Lie algebras, the Van Est works as follows. So given any cocycle on the Lie algebra, we integrate to a group cocycle. But derivation can be viewed as a cocycle. And we can integrate to a cocycle here, which will produce a multiplicative vector field. So that's just a very, very general idea. And then one can show that what is nice about this vector field, that the zero locus of this vector field is precisely G0. And in a sufficiently small neighborhood of G0, this vector field has the Euler form, and the eigenvalues are the same as for the epsilon. But actually, there's a small, it's an isomorphism between G, viewed as a module over epsilon, and this one. And actually, this can be shown by use of the exponential map around, for a neighborhood around identity map. And then we can extend it to some neighborhood of G0 by use of the multiplicativity property. And let me finish now. I have only 1 minute or 2 or whatever. Let me finish now with the remark that just you see here, just by hands, we produce 2 different structures. First of all, a semi-formal manifold, which is smooth on G0 but formal in the transversal direction. On the other hand, starting from the same graded Lie algebra, we produced some usual manifold or super manifold with a multiplicative vector field, which looks like an Euler vector field around its zero locus. And this gives us the hint that the right notion, global notion of Z-graded manifolds, this can be 2 different notions. One that Vladimir explained, and the other one is the following. So we have a super manifold together with some vector field, which we call the Euler vector field, such that in a small neighborhood of its locus, it looks like the Euler vector field, really. So it's the sum of degrees times, so the Euler vector field must look like the sum of some m, I, xi, d by dxi, the coordinates, right? So it's always possible to find coordinates such that this vector field looks like that. And in a neighborhood of the identity map inside G, this is given simply by the exponential of the Lie algebra. Otherwise, we just translate this just by use of left translations, for instance, and using the multiplicative property. What is interesting that if you require that, then it might happen that your manifold, so the zero locus is not connected. So it consists of several connected components. And around each connected components, these values are the same, so they're invariants. But for 2 different connected components, they can be different. And the example is very simple. So let's take, for instance, RP1, which is can be, okay, this is just a circle with 0 and infinity, right? And here, suppose here we have the coordinate x, and here the coordinate y, which is 1 over x. Okay? And now let's take the vector field, which is in homogeneous coordinates, is written as follows. So this is z0 d by dz0 minus z1 d by dz1. So this is again given by the action of h element in SL2 on the projective line. And then, so this is a homogeneous vector field. It means that we can write this in coordinates x and coordinates y. And one, you can check that in coordinates x, it can be written as minus 2x d by dx, so the around 0. And the same as minus plus 2y d by dy around infinity. Indeed, what happens? So our epsilon has two connected components. So the zero locus of epsilon has two connected components. And around each connected components, these integers are the same. So here is 2, here is minus 2, here is 2. But for two different components, they're different. So actually, it's a nice feature. For instance, we can look at many examples. This can be projective spaces, flags, whatever. So just knowing the Lee's theory of finite dimensional simple Lie supergroups, we can produce just a huge number of examples with non-trivial gradients, which generalize this one. Okay, that's all what I wanted to say.